So I remember not long ago, I was sitting at the back of lecture rooms, listening to lectures in this very university, just like all of you. So I'm very happy to actually talk to all of you. In fact, I think when I was writing this talk, I was basically designing this talk to myself, what I would have wanted to know as a person who started doing engineering and then later on switched to mathematics. So I hope you can take something out of this, whether you want to do mathematics after this or not. So this was actually part of the abstract that I posted, that I sent to Isuru when I was asked to give a talk. So this actually captures part of the things that I want to talk about. So what does this say? So if humans had lifespan of 500 years, the way we would educate ourselves would be different. You can probably all agree on that, right? But what it does is it frames things differently. It frames things differently from how we are usually used to looking at things. And we can start to imagine, okay, if we lived more than, let's say, 500 years, maybe we should learn something initially in the first 20 years, then take a break, do a little bit of more work, and then when you're 50 or 60, then you start learning more about something, right? We would restructure everything drastically, right? We have to completely reimagine how we would do this. And that's going to be part of what I'm going to discuss, and how the necessity of imagination becomes important in mathematics and beyond. So this is also part of the theme. So that's basically what this part of the abstract was about. Okay. So the outline, first I'm going to go through some ideas about mathematics, and then I'm going to go into some concrete math. Some things that you have already probably covered, things like linear algebra, but maybe with a different perspective on things. And then some things that are within your grasp. So things like quantum mechanics, I think you have the mathematical background to actually learn this at this point. So I'll go into that a bit very quickly. And then some things which are probably not within the grasp as of now. And then I'm going to go into some other important considerations, some stories that I think I should say. And after that, I'll go into how you can learn these things by yourself, probably, things like that. Okay? So this is how the talk will go. So let's see. So the first thing is a question. So when you read this stanza, right? Stanza, whatever, paragraph. What comes to your mind? Can you read this and think about it and let me know? Any ideas? Can be wrong. Just go for it. I mean. What comes to your mind? Is some complicated nonsense? So I know it's hard to extract answers, so I'm going to just give my own answer. This is the first thing that comes to my mind. The cat was chased by a dog and knocked over an umbrella, right? But what's the point? So there is some complicated language which avoids the use of the word cat, dog, and umbrella, right? And it's very hard to explain when you don't know what a cat is and a dog is. If you don't know those definitions, right? It's very hard to actually process this thing even, right? So a definition can be associated to something called a concept cell. When you study what's happening in the brain, there's this idea of a concept cell or a Jennifer Aniston cell. The reason it is called this is the guy who first did these experiments to see whether there is association that can be monitored through fMRI in the brain, was using Jennifer Aniston's pictures, the name, other pictures with in it, and some even people saying this, and then detecting that, okay, in the brain this is firing when this is. So there is something with association, and these cells help us think, imagine, remember, right? There is a Pavlovian aspect to it, if you know what it means. So when you're even when you're training animals, right, you see that, okay, they associate things. You can ring a bell. So Pavlov was this guy who rang a bell, and every time he rang a bell, the dogs that he was training basically thought that, okay, I'm getting food. And what happens is eventually, okay, you ring the bell, but don't give them food, but the dog is still salivating, right? So you get conditioned, right? Okay. So that aspect is also there, okay. So here's another definition first. So let's say there's a statement like this. Let's say that this is simple language. So the simple language statement is there were no people who did not know at least one person who knew the president of the society. So let's say there's a president of the society, and not everyone knows that person, but everyone knows at least one person who knows that person. Now that's hard to describe in usual language. But you can draw a graph like this and place the president in the middle, and like everyone who knows each other is connected by some edge, and there's some imagery. And we can say that, okay, this is equal to saying that we can define a notion as the connection degree of the president, which says that, okay, like if you can go through this graph by n amount of edges to this person, that's the connection degree, n, right? Okay, so then it's easier to say the connection degree of the president is less than 3. So here's the question. How do you say in simple language that the connection degree of the president is less than 5? How do you say that in like language like this? Can you think about that? How do you say this? There were no people who knew no people who knew no people. How do you do this? This is hard, right? Which is why we don't even like think about that. Unless we know something called connection degree, then we can easily map this, right? So simple language leads to confusion sometimes, complications, potential misunderstandings, right? Okay, so here's another idea. Simple language is actually too ambiguous to explain actual ideas. So there's this famous paradox called Bertrand's paradox. So it says, consider an equilateral triangle inscribed inside a circle. So you can imagine some circle within which there's an equilateral triangle. Suppose a chord of the circle, you know what a chord is, I suppose, right? Take any 2 points on a circle, join it. Is chosen at random. What is the probability that the length of the chord is longer than the side of the triangle? So okay, this is much harder to do. So let me first tell you, this is one answer you can give to it. And let me explain why this is an answer. So there is rotational symmetry of the circle, right? So what I can do is first I will rotate the triangle so that it hits one of these edges. And like if you want to study the space of all chords, right? The space of all chords will be like, okay, you take 1 point and draw all the chords from it. And then if you just rotate this picture, that captures all the chords, right? Okay, so we only have to study this, and the rotational symmetry will do the rest for us. Okay, so in this case, what's happening? All of these chords are longer than the sides of the equilateral triangle, while these are shorter, right? And we know this is 60 degrees, so the probability is 1/3. This is clear? You're following? Okay, cool. Here's another answer. So we still have the rotational symmetry. So what we are going to do is we are going to draw a line like this, right? And draw all the chords which are perpendicular to that line, right? And again, we can rotate and we can get all the chords. And like a similar construction can be done like actually you can get all the chords using this, if you think about it, right? So now what's happening is if you take these two lengths, this is like, this is half of this entire length, which means that the probability should be half. So what's happening? Well, if you check this same thing on Wikipedia, just like Google for Bertrand's paradox, you will see a third answer, which says it's 1/4. So the point is that natural language that we use in day-to-day life, it's too simple to write these like statements in an unambiguous way. Like you can't define probability measures to be slightly technical. You can't define what it is to be a probability on uncountably many things in like the normal day-to-day language that we use. So it's too simple. So natural language is too simple to write unambiguous statements on some things, right? Languages are limited, and they limit us. They limit us, that's important. So there's a lot by Noam Chomsky, who is this like linguist who went into like how the brain is basically like structuring how we are viewing the world. And it is that structure which like makes us learn things in certain ways, all these things. And so the more complicated the language is, the better. And of course, like now you understand I'm talking about mathematics, right? So the more complicated, the more richer the language is, the better we understand things. And there's this idea of Occam's razor, which says, okay, like, in order to explain something, you need to like cut down things to make it as simple as possible. You should like have the simplest explanation possible, which captures all the aspects. But in order to cut down to that, first you need to explore all the different possibilities. So you need complication in order to achieve simplicity. Okay. So there's this famous quote by this poet Goethe. Mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it is something entirely different, right? So, and there's a lot of truth to it if you like really go into it. Here's another one. Can you translate this? So you can imagine a ball. You exert forces onto it, and it compresses as you exert forces in different directions. When you exert forces in one direction, it compresses maximally. In the other direction, the compression is less. Okay? Okay. So you look for the compression. Okay. So you have the maximal direction, and then you have the orthogonal plane, and you start looking at what are the other directions in which you have the second maximal direction. So already orthogonal is a mathematical term, right? But okay, and then the idea is, okay, so the compression achieved was half of the maximal direction in the other second one. So how do you say this mathematically? Hint, the stress tensor is a symmetric matrix. Does that help? Don't worry too much about it. This is probably like, I'm way overreaching probably, like it will take me also some time to. Okay, so you can actually rephrase this as saying the ratio of the largest two eigenvalues of the stress energy tensor of the ball is 2. So the maximal compression direction is the maximal eigenvalue. And if you take the orthogonal things, then you get the other ones, the other compressions, right? So if you take the second largest eigenvalue and the ratio of the two, that's 2. That's saying that the compression achieved is half of the maximal, right? But because we have this mathematical language, then we can actually work with it in other ways. So how's your linear algebra? That's where we are going. So can you remember the spectral theorem for self-adjoint operators? Or something more simpler. So if you have a matrix A, which is symmetric, then A can be diagonalized, and there is a basis of orthonormal vectors. This you remember. Okay. If you remember, so here's an example of such a matrix, right? So here's the diagonalized matrix, and here are some basis change matrix. Okay, so now I'm getting technical. As I said in the outline, I will first get technical and things that you already know, but perhaps in a different viewpoint. Now the point is, in this construction, this basis change matrix, right? Well, this is the eigenvector corresponding to this eigenvalue. And this is the eigenvector corresponding to this eigenvalue, and so on, right? So in this case, the ratio of the first two eigenvalues, that's 2, right? So this is stress energy tensor of that type. Okay. So when you see this, what comes to your mind? What are the first things which like the Jennifer Aniston cells, what are the first things that come to your mind? Think about it. So this is how I am trained now after like thinking about it for a while, even in undergrad days. This is how I used to see things like this. So you have this basis change matrix, and then, so it's basically 3 eigenvectors, the eigenvalues, these are a bunch of zeros, and then these are these eigenvectors. That's what this is, right? Okay, so let's put in an eigenvector into this. So let's put in the second eigenvector v2. So what happens, you take the dot product of this and this, but they are orthogonal. They are orthogonal vectors. So it's 0. If you take the dot product of this and this, well, it's the same vector, so you get 1. It's an orthonormal basis. And you take the dot product of these two, you get 0. Okay. So when you do this operation, you get basically this vector. Then it goes into the next matrix, right? And what comes out after multiplying by that, it's basically the second eigenvalue times the same thing, right? This is simple enough, right? You're with me? Okay, good. And then what happens? Then you throw it into this matrix, but then what happens is, okay, you're throwing this into this matrix. What's going to happen? You'll get lambda 2 times just the second eigenvector. This is like easy to process, right? So when you see this picture, it's easy to process, right? Okay. So basically that's what's happening in like all these matrices, right? All symmetric matrices, basically this is a good way to think about them. It's basically you have the basis change matrix which are composed of the eigenvectors, then you have the eigenvalues, and then you have the eigenvectors, right? Okay. Abstractly you can write it like this also, right? This is a different way of writing this, right? I mean, I'm sure you're all familiar. So if you have any vector, W, you can write it in terms of the basis vectors, and then applying A to W is basically, okay, once you decompose these things into these basis vectors, you're just multiplying by the eigenvalue. That's it, right? So it's getting technical, okay. You're with me, okay. This picture, do you understand what's happening here? So V1 is basically this vector, right? I mean, this vector. So it's just the vector pointing upwards. We know what this means, okay. So if you have V2 and V3, these two, I've drawn them, right? Another way of thinking of this is, first this basis change vector, basically it takes this vector to this and this vector to this, right? First you do that. And then you just scale along the axis according to the eigenvalues, and then you flip it back into the original basis vectors, right? That's the picture, right? This is the picture you should have. If you don't have it, this is the picture you should have. Okay. So these are all, so whenever you see something like this, all these ideas should map with that cell, you know, or this structure of cells which are like forming in your head. And this is the point of like learning mathematics. Like you learn mathematics so that like you're able to like map all these ideas. You can think about the same thing in different types of ways, right? Okay, so let's go one up now. So let's look at infinite dimensional vector spaces. Some of you may have already done like Fourier analysis, maybe in people in your 4th year or something. So if you consider periodic functions, right? Well, you can add two functions. You can multiply it by scalars, real scalars, complex scalars, right? It's going to be a vector space. You have the 0 function, right? And okay, so you have a vector space of these smooth functions which are periodic functions on an interval, okay? There's actually an inner product on this space of functions. So this is the inner product. You basically integrate. So if it's complex valued, you take the first function, the second function, do this. And in my mind, this is similar, somehow it's mapped similar to how the dot product happens, right? So now I can think about this, how I'm like visualizing that picture with like, okay, I'm separating bases, all that. So these things are all connected now, okay. Oops, okay. So there's a self-adjoint, okay. So there's a self-adjoint operator. So if you take this operator, which is differentiation, differentiation appears everywhere in engineering, in maths, physics, everywhere, right? So if you take the operator which is differentiation and also multiply it by 1 over y, then you can actually show that this is a self-adjoint operator with respect to this. And I'm not going to go into the details of that, but this is a very simple computation you can try if you want to. Perhaps you have already done it if you've done Fourier analysis. And what are the eigenvectors for this? Well, these are the eigenvectors, e to the I kx, right? So if you differentiate e to the I ax, what will you get? You will get I a times the same thing, right? So these are the eigenvectors with the eigenvalues k because of the 1 over I is there now, right? Okay, so this is a slide. You can actually show this yourself. I mean, that this is self-adjoint operator. Okay, so what if I do this? Okay, so now I want to study this operator like I study this matrix. So what do? I first diagonalize my operator, which is this differential operator, right? How do I do it? I have to first, okay, I'm going to take the vector I have. This is the vector I have, right? I'm going to project it onto the orthonormal basis. Now, what is my orthonormal basis? It's this, right? So the projection is given by doing this, right? I mean, this is the inner product, right? Okay, so you do this, right? Now, this is the Fourier transform, right? So I'm diagonalizing my operator. After I diagonalize, I just multiply it by the eigenvalue. So I multiply it by the eigenvalue. And then I have the summation over the, so you have the summation over the eigenvectors. So that's the summation over the eigenvectors, right? So this is Fourier analysis, right? And it's linear algebra. Now the problem was I only realized this maybe in like 4th year. Whereas I learned linear algebra in my 1st year. And then I learned Fourier analysis in my 2nd year. But it took me till my 4th year to see this. And there's a problem, right? This is a problem, right? I mean, maybe, okay, did you already know this picture earlier? No, this is new? But the point is, then it helps us to think about Fourier analysis in terms of linear algebra. It helps us to think about linear algebra in terms of Fourier analysis, right? It helps us to think about these things differently. Okay, so you can even define fractional derivatives now, right? So what does it mean to differentiate half times? Like you can differentiate once, twice, integer times. What does it mean to differentiate half times? So that's a fractional derivative. You just, I mean, we know now that this makes sense if this is an integer, but I can always like take other powers, right? So that's a fractional derivative. And in fact, there are electrical components like fractors, you can like look this up, which behave this way. There are physical things where actually the differentiation is only done half times. That's the model, right? So these are ideas that you can extrapolate like once you like have a well-defined notion of like what's actually happening here. And of course, there's other things like you can do non-periodic Fourier transforms. It gets complicated, but there are similar pictures here. But I want to stick to the point. The point is that, okay, so these are the non-periodic Fourier transforms. There are more relations. These are now, I'm just saying facts, not expecting you to, yeah. So here's the question, why do, okay. So actually I realized later on that, okay, in my 1st year, I saw this, there was a tutorial which had this thing. The Fourier analysis thing was there in the 1st year. But somehow it didn't register. So why don't the important things register in our heads? This is a question. Maybe you guys must have also seen this example. Actually, I was talking to someone, he was telling me that this example was there in the 1st year, but it didn't register. So if it is pointed out, perhaps it might register, right? Okay. And what happens when they are pointed out is there's a network of connections which are formed in your head, which helps you to think about things in different ways, right? Okay. So then at that point, you have your Jennifer Aniston cell, which links to another Jennifer Aniston cell called the Fourier analysis. There's other things which are related to linear algebra, which I also saw in the 1st day actually, like error correcting code. But then again, error correcting code was done in the 4th year, and then it registered, okay. Then I realized, okay, this is connected to linear algebra, and then I realized the importance of this. Quantum mechanics is not something that's done, but actually there's a big network of ideas which are intimately related, through which you can think about all the other things. Yeah, so there's like nice stories about this Hamming code. But I'm not going to go into it now. But so, okay. So the point is, there are connections which I think that we should be exposed to, but somehow through the structure that is here, and it's not just here. I've talked to people in other places also. Like it's not just some problem like here. This is a bigger problem. And like really what I was thinking is like, how can you address this? That's what I was thinking about when I was writing this talk. Because like if I were to talk to the guy that I was sitting in the room years ago, I would want to tell him, okay, there are these connections, make these connections. That's what I would want to tell him. Okay, so 2-minute crash course in quantum mechanics, just to show, like, give a taste for it and to like maybe motivate you to like learn it by yourselves. So let's say that you have a hill like this, right? And you have, let's say, a ball like this here. Now, okay, you can write the energy, right? Kinetic energy, potential energy, right? Okay, you have, let's say, a constant energy. There's no friction. So what's going to happen? This is going to like roll like this, right? This thing will never end up here, right? That will never happen, right? Okay. So let's do a simplified model. Like this sort of model appears so when you neglect the y dot. I mean, you have like similar models in like when you study electrons, even in like transistors, semiconductors. And it's still a good enough picture to have, you know, like this like ball rolling. Like you can just ignore this y dot squared. I'm being very, okay, here. But it's a good picture to have, and like the things I'm going to say are like more or less qualitatively accurate. So, so another way to say that the particle is here, a strange way perhaps, is to say that the particle is here with probability 1, and the particle is here with probability 0, and the particle is here with probability 0, and so on. And it's a strange thing initially, right? So we can say that this is a delta function, which means that the probability is 1 here, and everywhere else the probability is 0. So if I ask the question, now where is the particle? Here's a different way to say it. So, okay, I mean, the particle is here, x1. A different way to say it is integrate this for this function delta x1. Whatever that means, integrating multiplications of delta functions, very iffy. But you can imagine, okay, so everywhere else it will be 0. At this delta function, it will pick up the value of x1. Roughly something like this, right? Roughly. So this is actually the weave that you take in quantum mechanics. Now, why do you do this? So in quantum mechanics, there's like two modes initially when you're learning this. First, when you're observing the system. When you're observing the system, it will act like a particle. It will more or less act like some classical mechanical system. So what you're seeing is this thing is rolling, so the delta function is just going, moving. That's what you'll see, right? Classical mechanical, okay. So this is a rephrasing of classical mechanics, just delta functions moving about. Okay. What's actually happening is these delta functions, when you're not observing it, or there's no interactions, what's happening is they're going to start evolving in different ways. So if you start with t equals 1 here, sorry, t equals 0 at time 0 here, what's going to happen is the probability of where the particle is going to actually change. And it is probabilistic. So if you repeat the experiment many times, this is the distribution of, okay, so here's an experiment. You set it up at t equals 0, you stop observing, you observe at t equals 1, right? If you do this experiment 1,000 times, you will get a distribution of values like this. It's not one value. It's not deterministic in that sense. Determinism is gone, okay? So, okay. So it's going to evolve like that. And you can say, okay, I know that the particle is here with probability this much. That's what you actually say in quantum mechanics. Okay, so what happens is actually, like this wave function evolves according to this equation called Schrodinger's equation. You basically take this energy thing and think of it as some differential operator. You can multiply by this potential. That's just multiplying by a function, that's fine. You take this, and so the x dot squared gets replaced by take a derivative with respect to x divided by I squared. And we call that a momentum operator. And what happens is, this is how this wave function is evolving if you solve this PD. And actually a particle starting here can end up here. And that's called tunneling. And if you look at like tunneling diodes and things that you even use, that's what's actually happening. These things, tunneling happens. So these are things that you're actually using, but maybe you're not exposed to, right? Why is that? Okay, so this is the probability that the particle is inside a certain interval, right? So we call that the position, this is the probability of the position operator. So the x here is the position operator. The momentum operator, if you want to see, okay, what is the momentum of this particle at this point, and if you do some experiment to detect this, what will be the outcome? Well, it will be, well, we can say that the momentum, this is the probability of that momentum being that value, or like being in that interval of values. Okay, now maybe this doesn't make sense. Or you're following, okay, I don't. So anyway, but the point is, there is this, this is actually the Fourier transform of this position operator. Now the momentum operator is going to be the Fourier transform of the position operator. It's strange initially. Of course it's strange. Quantum mechanics is strange. But once you get used to it, it becomes easy. And then you can maybe use even that knowledge to make your linear algebra easier. So this is something that happens as you like start learning these things. So I just wanted to like tell you about this. Okay, so maybe you're hopelessly lost now, I don't know. But actually there are interesting things like Heisenberg's uncertain principle here. Like, okay, so if you know Heisenberg's uncertainty from like A-level chemistry, what does it say? Okay, if you know the position, then you don't know the momentum, right? So okay, if the position is a delta function, what is the Fourier transform of the delta function? This, right? Yeah. So that's equal probability, right? So you don't know where it is. That's one interpretation of it. Okay? So there are like, you actually only understand what these things are when you understand the language, which is why we want to study mathematics, which is why we want to understand it in the proper language in which it can be understood. Okay? So, okay, and of course, so you have time frequency, time domain, frequency domain ideas, you have position momentum ideas, or you can just say, okay, we are just picking an orthonormal basis in which the differential operator is diagonalized. And then we are working on that domain, right? So these are all like ideas which are tied together by mathematics, right? Okay, and it's a very rich subject. So here's another story like this. Now I'm not going to go into much details, but if you've done vector calculus, and if you haven't done it, don't worry about it. You will probably learn it very soon. You're in good hands. So okay, so let's say you have these grad curl div operators, if you've seen them. I'm going to label them as d0, d1, d2. And there are two main relations that you learn, which is that the curl of the grad of a function is 0, always. And the divergence of the curl of any vector field is also 0, always. And this can be relabeled as this thing. I mean, it's the same thing. But now it's sort of unifying, right? It's just one equation which captures the information. Okay, here are three important results. This is the fundamental theorem of line integrals, the first one. And then you have what is Stokes' theorem and the divergence theorem, right? But there's a common structure to this. So you have a one-dimensional integral of grad, which is the d0. And that is just going to be what is inside this evaluated at the boundary points of this C. So this is an integral along a curve. You're just evaluating what is here at the boundary points, right? That's what's happening. Similarly, here you have some surface, some two-dimensional surface with a boundary. You take the curl of f, right? And that integral over this two-dimensional surface is equal to just evaluating this or integrating this at the boundary, right? So same thing with the divergence. You can think about that one, okay? But there's a common structure. So you take this d of f, integrate it on the, let's say, the k-dimensional space. And what's happening is, okay, that's equal to just integrating it on the lower dimensional boundary. Right? There's a common structure. And that's not a coincidence. Actually, there's a theory which does this in any dimension. And what we see initially is just this, like, yeah, we are introduced to that structure initially. So in the faculty, so I mean, was doing elect, so we did like electromagnetism using this language. In civil, people use like fluid mechanics with this language. But what happens is like, okay, like you develop this language well enough, and suddenly you can say things about like all particle physics in this language, actually. In fact, what happens is, so in electromagnetism, there's the electromagnetic tensor, which captures the electric and magnetic forces, and you can reinterpret that as the curvature of a vector bundle. I'm not going to explain what that means, but there is some like completely bizarre world which you can slowly learn if you want to. So yeah, so the standard model of particle physics is basically written in this language. Like all particle physics that we know and can explain can be like in like Earth and so on, can be explained using the standard model, and it's written in that language. And so there's a big like connection between geometry and physics. And okay, I think I sent the wrong slides maybe. So here's something that Michael Atiyah says. Okay, so you know in like vector calculus, you learn a lot of like geometric things, but you build this like algebraic structure to study them. You have grad curl div, but it's capturing how like all these like things are acting in different directions. So Atiyah says this: algebra is the offer made by the devil to the mathematician. The devil says, I will give you this powerful machine. It will answer any question you like. All you need is to give me your soul. Give up geometry, and you will have this marvelous machine, right? And there is a point to this, of course. Like algebraic machinery allows us to like compute things very easily. We can even put it on computers, and it's helpful. But if you don't understand what's happening, what are you doing, right? Which is why we learn vector calculus like really well, right? I mean, we are taught really well vector calculus. So here's another idea. Okay, let's see how much time do I have now. Okay, so I'm restructuring the talk now in my head. Similarly, there's an idea of metrics on spaces. So this is a circle. It's a deformed circle, but it is like some deformation of a circle, right? I'm changing the lengths between all the points. So now the length between these 2 points is L1, the length between these 2 points is L2. So on the two different circles, the lengths are different, right? So the metrics are different. On a sphere, how do I define the length between points? I can take the path that is the shortest path from one point to the other. That shortest path is called a geodesy. And then the length of that geodesy can be called the length, right? Or the distance between the points, right? On Earth, this is how we travel, right? If we want to get shortest path, flying planes. Okay. So here's the story. So if you know Newton's first law, what is Newton's first law? If there's no unbalanced force, either the particle is stationary, which is constant velocity, of course, but if not, it moves with constant velocity along straight lines. And that's a geometric term, right? What's a straight line? You know what a straight line is, but that's geometry. So geodesics on Rn, right? Okay. So let's consider the picture. Now this is the truth as we see it, right? Okay. Let's imagine that this is the sun. And okay, so the sun, okay, so the Earth goes around the sun roughly in a 2D plane. So let's assume that space is 2D just to make this easy for ourselves. And imagine time as this axis going up. Now the sun is moving up, right, in time, because we are going to fix the frame to be centered around the sun. So the sun doesn't move because it is centered around the sun. So in time it moves. Okay. So this is the sun moving. And the Earth will basically go around it in a helical orbit, right? That's what's happening, right? Okay. So what does Newton say? Okay, now why is the Earth not moving in a straight line? Because there's an unbalanced force, right? If there was no unbalanced force, then the sun and the Earth would both go up like this in this picture, right? What's happening? There are forces, according to Newton, and so this force creates this orbit, right? What does Einstein say? Einstein says, okay, no, the geometry is not that of Euclidean space. Like you can imagine a 2D sheet versus a sphere, right? The geometry of the 2D sheet is different from the sphere. Now, it's hard to imagine what's happening in 4 dimensions, but you can write equations for it, and you can show that, okay, what's happening is space-time is curved, and so light, which doesn't have mass or anything, it travels along geodesics. And the geodesics aren't straight lines. And we actually observed that. Like, you can observe these things, that light actually bends if we think of it as Euclidean space. The point is, it's not. So you have to like completely reimagine what's happening. Just like you reimagined what classical mechanics is, like, okay, you say that, okay, instead of the particle being here, it's a probability distribution, right? Similarly, you have to like reimagine what's happening. And that's how you can like come up with ideas, and then you have to prove it, of course, but this is the start. So this is something Witten says. The beauty of Einstein's equation is just as real to anyone who experienced it as the beauty of music. And actually, people have done experiments with fMRIs to see in the heads of mathematicians what's happening also. So this is a, and they see that like actually there is some similarity like this. Okay, so now I'm going to like go really fast and skip right to the end, just because time. Yeah. Okay. So here's maybe something I want to say. Oh. Okay. This also doesn't make sense now. So I think what we need is you need to reimagine. You need to reimagine what your education should be. And that's because the decisions that are made in order to, okay, so let's consider, okay, how is a syllabus crafted? How do you choose what the engineers in Peradeniya learn? This is a hard decision, right? There are many interests. The state has an interest. Okay, we need to create engineers. The people in the engineering faculty then take that responsibility and think, okay, this is the best thing for like most of the people in order to produce engineers. But if that is not what you want to do, if you want to like switch to maths or physics, right? And people have switched to many things. People have done economics after doing engineering, right? If that is who you are, then you need to reimagine your education. So, and I mean like first beyond this, like you need to like reimagine who you want to be. You need to like reimagine, like, I mean, even if you like think that you want to become an engineer, it's still a good idea to think, okay, like if I become a physicist, how will I do that? And what could I gain from that, right? Things like that. You have to think about these things when making these decisions. Don't be like, I mean, close in this, I mean, maybe you should like be exposed to that idea, like that you should reimagine yourself. But anyway, so, if you do want to reimagine yourself, then there are ways in which you can learn some of the things that I was discussing. Well, there are competitions organized, right? I saw you're organizing some competitions. That's great. But then you can do projects and research related to the things that you want to pursue later on. I remember, like in my third year, when I was thinking about like how to do a final year project, I went to first like Dr. Ruan, and he said, and I told him, okay, I want to do a math project. And he said, okay, like I don't have math projects, but maybe you can talk to him. So you have to talk to people. And then they will help you, you know, like people here are really helpful, and they will help you figure out things that can be helpful here. You can do online courses. A lot of my friends and myself, we learned a lot of these things. Actually, I learned like most of general relativity while I was an instructor here. You have to just learn it yourself. There are plenty of resources available to you. You can take reading courses with people. You can form reading groups on your own. You don't need to like wait till like someone forms a reading group and says, okay, now there's a reading group, come. No, the students, you can organize with your friends, right? You can organize. You don't need some formal backing in order to do it. Just, right? You have to throw that attitude out of the door. So there's this like overly simplistic view, you know, like, okay, let's say we are, that all students can be put into like one cluster like this. So let's say this is Pera, why not? I mean, I'm not saying it's Pera, this can be Pera as well. Okay, let's say this is Pera, okay. And let's say this is MIT. Right? This is an overly simplistic view, right, of students as like statistics. But this is how, like, I mean, it's hard to like plan syllabuses, and sometimes this is how a syllabus is planned. And I'm not saying that this is how like they are planning it. This is how like people all around the world are planning it sometimes, and this is how like people in the UGC or who have control over your education are planning it. And that's the problem. Like someone else is in charge of your education. That's a big problem. So and then you will get exposed to this. But what if you're here? You want to learn more. So then reimagine what you're doing. Teach thyself. In fact, even if you're here and here, still teach thyself. Teach yourself. That's what I have to say. And how do you actually know this is where you are? Most of the time, like, we have communication problems. I know, like, in the first year, like, you probably know, like, here we have a lot of people with language problems. But then there's this other interpretation of what a language problem is, that the mathematical language, right, if you don't understand the mathematical. I remember, like, in first year, like, the very first lecture, actually, like, Professor Susanta told us, you know, if you do your maths correct, then everything else will fall into place. And that was good advice, actually. So, and then very quickly, I will talk about applying for higher studies in mathematics and physics. So I think the key thing to do is talk to people. And you have to like talk to many people and figure out who's in your own wavelength. So this is not, I'm not saying you should talk to these people. I'm just saying that these are the people I talk to, right? So I talked to Dr. Pantelian, Dr. Sanjeev Maitripala, and I mean, basically because I was doing my final year project with Professor Godley. And they really helped me, like understand what to do, how to go along these paths. Find others with similar interests. A lot of my friends, so Dhananjay Liyanage was a contemporary, and he basically switched to physics. Anurad Ekanayaka was an instructor who came here from Moratuwa, and he switched to math as well. This guy was from the science faculty. There were many others I was talking to. And we basically like learned the same things together. And even doing engineering, actually. So, I mean, I did a lot of like group projects and things, but you just talk to people and figure out if you have like similar interests, you just do a project. That's a thing that I think is useful, not just in mathematics, whatever you want to do, right? So if you're applying, maybe you should think about like engineering research or some sort of research. Engineering research is good enough if you want to switch fields. Do your final year projects well. You can ask for a more mathematical project, as I said, you know, like talk to people. Tell them this is what you want to do. Then they will respond. I think like not enough people actually like do this, which is why I'm saying that. Okay, so when you're applying, you have to write all sorts of statements about like the statement of purpose. So you should already start thinking about those things. If you want to do these things, now you have to start thinking about them now. You probably know about tests that you have to take. So there are things called the GREs. Of course, this is not something I can discuss in like 10 minutes or something like this. I will probably end very soon. But the point is there are exams, and you should probably talk to people who know about these things. Probably some of the instructors in the maths department, or even Isuru can help you with these things. And really, but the main thing is you have to learn the subject, right? You have to learn the subject. So spend some time and you have to learn. So I used a lot of online courses, so I'm just going to like keep this here. So these are some online courses, like you can find the black ones on YouTube, and the blue ones are basically books. Then there are people like fields medalists, you know, like people who are at the top of the fields, have lectures on YouTube on like very elementary subjects these days. It's something that in human civilization has never been there earlier, right? Like, imagine like 500 years ago, you could access the top person in the field from, you know, like all over the world and learn from them. It's completely different now. So there are great resources now. So I will keep this, and probably this is the other thing. So I think quantum mechanics is something that like engineers learn everywhere. Not everywhere probably, but so engineers actually learn quantum mechanics. There is a, I think in the inertia of the system, it will take some time for, you know, like Peradeniya or like anywhere in Sri Lanka to like adopt this into the system. But that doesn't mean that you should restrict yourself. If you think that you're going to do something, even in like engineering. There are people, you can talk to people who did like certain branches of engineering, of course, that it's actually very important that they learn this. So they learn it later on. So just explore the world and figure out what you want to do. And I will stop there. Thank you.